welcome to The Explainer. Today, we're going to look at the world through a completely different lens. Think for a second about just how messy and chaotic human behavior actually is. We make totally unpredictable choices, markets fluctuate wildly for seemingly no reason, and societies are just incredibly complex. So, how do we actually find the hidden truths buried underneath all of that noise? Well, economists act as what I like to call data detectives. They use a highly specific set of mathematical tools to uncover the real stories hidden in the data. And the name of that toolkit? Econometrics.
Here is our roadmap for today. First up, what is econometrics? Second, asking the right questions. Third, population versus sample. Fourth, the law of consumption. And finally, estimating the truth.
All right, let's jump right into section 1. What is econometrics? Let's define the field.
So, formally, econometrics is the field of social science where economic theory, mathematics, and statistical inference are applied to estimate and measure economic phenomena. Okay, but what does that actually mean for us? It basically means this field isn't just about sitting around coming up with abstract theories in a dusty library. It is quite literally the act of measuring economic theories to see if they actually hold up in reality. It's where the theoretical meets the practical. And econometric forecasting is used absolutely everywhere. Seriously, if you watch cricket and you've seen the DRS, the decision review system that predicts the trajectory of a ball and whether it's going to hit the wicket, that is economic forecasting. Even something as routine as checking your local meteorological office's rain forecast before you leave the house relies on these exact same principles. It's all about taking past data to accurately predict future outcomes.
Moving on to section 2, asking the right questions. From theory to reality.
We definitely don't just use this math for sports and the weather. This math matters deeply in the real world. Consider some of the heavy-hitting research problems that data detectives actually try to solve. Do smaller class sizes actually lead to better student performance? Is there a measurable impact of gender discrimination on wages? What is the exact quantitative relationship between cigarette consumption and public health? These are massive, incredibly important questions that require rigorous quantitative answers, not just opinions.
And this brilliantly illustrates the ultimate goal of asking those questions in the first place, finding the causal effect. Imagine a randomized control trial out in an agricultural field. The question is simple. What happens to the rice yield if the application of fertilizers goes up? We don't just want to know if fertilizer and rice happen to be in the same place at the same time. We want to isolate the exact direct causal effect that variable A has on variable Y.
To nail down that causal effect reliably, every good data detective follows a strict scientific method known as classical techniques. It's basically a 6-step process to solve these quantitative mysteries. First, you state your theory or hypothesis. Second, you specify how exactly you're going to test it mathematically. Third, you roll up your sleeves and obtain the data. Fourth, you estimate the results. Fifth, you run inference testing to make absolutely sure your results are statistically sound. And finally, step 6, forecasting the future. Let's dive into section 3, population versus sample. Gathering our clues.
So a absolutely crucial point here is understanding the difference between these two. The population is the entire set of items, the whole data pool. Let's say we want to know if studying science in high school leads to better economic returns for males in urban India. The population would literally be every single urban male in India. But here is our core limitation. We obviously can't interview everyone in a population. It's just impossible. So instead, we must draw a sample, a smaller, manageable subset, to estimate the parameters of the whole.
Once we have our sample, what do we actually do with it? Well, many people confuse these two terms. Correlation just measures the strength of association between two variables, like noticing that people who carry umbrellas also tend to wear rain boots. But regression? Regression is a real game changer. It's the true detective's tool. It allows us to estimate or predict the average value of one variable based on fixed values of another. Regression doesn't just say two things are related, it helps us predict the outcome.
Which brings us nicely to section 4, the law of consumption, translating the math.
Let's slow down for a second and translate the Greek letters you're looking at here. This is the fundamental psychological law of consumption. The big idea is super simple. C equals F of I. Consumption is a function of income. The math basically states that as your income goes up, your consumption goes up too. But notice the rule at the bottom. The change is between 0 and 1. Meaning, if you get a raise, you're definitely going to spend more money, but you will only spend a fraction of that new income. You'll save the rest.
Now,
What's really fascinating is that tiny letter u added to the very end of the equation. This is the stochastic error term. It's essentially the mathematician's way of admitting that human behavior is incredibly messy. We aren't robots. Maybe you got a raise, but your car immediately broke down, so your consumption changed for reasons completely unrelated to your income. That U accounts for all the unexplained errors, random events, and chaotic noise in our clues, the whole shebang.
And finally, Section 5, Estimating the Truth, Drawing the Line.
Meet the PRF, the population regression function. Think of the PRF as the absolute truth. These are the true fixed parameters of the entire population that we are desperately trying to uncover. If we somehow had unlimited time and money to survey every single person on Earth about their income and consumption without making a single mistake, this is the line we would draw. But as we established earlier, we can't do that.
So instead, we rely on this, the SRF, or Sample Regression Function. Because we can only draw a small sample of the population, the SRF is our best guess. Look closely at the notation here. You'll see a little hat over the Y. We call that Y hat. Whenever you see a hat on a variable in econometrics, it means it is an estimated value, not the absolute true value. We are doing our absolute best to guess the PRF by using our SRF.
See the solid line? That's the PRF, the true hidden population line. The dashed line is our SRF, our estimated best guess based on our sample. Notice how they aren't perfectly aligned? There is a gap between the actual data points and our estimated line. That gap, labeled with a U hat, is our residual. It is quite literally the physical measurement of our error. It's exactly how far off our best guess was from reality. Since our goal is to draw the most accurate line possible, we obviously want to minimize those errors. We want to make them as small as possible. But we run into a critical math trap here. If we just add up all our errors, the sum of U hat, we run into a huge problem. Because some data points are above our line, giving us positive errors, and some are below our line, giving us negative errors, if we just add them up, they simply balance each other out to zero. A completely terrible model could look perfect just because the positive and negative mistakes canceled each other out. No way we can rely on that.
So how do we fix it? Well, here is the ultimate data detective trick. We square the residuals. By squaring the errors, two amazing things happen. First, a negative times a negative is a positive, so they no longer cancel each other out to zero. Second, and this is the best part, squaring properly penalizes massive mistakes over tiny ones. An error of 2 squared is just 4, but an error of 8 squared is 64. Squaring places a much heavier weight on the big errors, forcing our regression line to stay closer to the center of the data.
It's a brilliantly simple yet absolutely powerful mathematical trick that allows us to find the truth in a noisy world. But I want to leave you with a final provocative thought. If squaring errors changes how we mathematically penalize mistakes, putting massive weight on huge outliers and forgiving the tiny ones, how might placing different weights on errors alter the way we view the world's data in our everyday lives? Do we let massive outliers skew our perception of reality, or are we drawing the most accurate line through the noise? Definitely something to think about. Thanks for joining me on this explainer, and keep asking the right questions.